All right, now that we've got the moisture in the atmosphere, we're going to take it and make some clouds and precipitation. So we've learned a lot about how moisture moves around in the atmosphere and processes it deals with. Well, now we're going to deal with that and turn that into clouds and precipitation this week. So with that, how do clouds form and how does precipitation form? Well, we know water vapor is invisible, and there's water vapor in the air every day. So if you even look outside and you see a very sunny day, not a cloud in the sky, there's still water vapor out there. In clouds, on the other hand, you can see them. They're condensation. They're water droplets. So there are things that allow clouds to form. You would think, oh, relative humidity, 100%, immediately water vapor droplets will form. Well, unfortunately not. What happens here is that the saturation vapor pressure over a curved surface, here we go, curved, very small curved, is much, much higher than it is over just a regular flat surface. So where 100% relative humidity means something over a flat surface, think about it. An initial water droplet is extremely tiny, hard to even see by the naked eye. That is going to be really curved. So that means that curve is going to allow a lot of water to get out of that droplet, so you wind up losing it. Well, reality is you need about 300 and some percent relative humidity to form a cloud droplet. However, there are some things that make it possible. Something called hygroscopic nuclei. Basically make a solute with that water droplet. They turn it into where you need 100% or less, literally, to get relative, to begin to have condensation and cloud droplets form. So that, where the curvature effects make it extremely difficult, the solute makes it possible. So they just work together, one working to beat out the other, and eventually the solute wins. We wind up with clouds. Now, the next thing is, guess what? If there's nothing to freeze a water droplet, they're just tiny little droplets, so they have lots of kinetic energy in them. So it takes a lot to freeze them. What happens is you need an ice-forming nuclei. One of those type of things might be salt. Some kinds of dust are ice-forming nuclei. But what that does is it allows supercooled water still to exist down to about -9 or so temperatures. At that point, if there's ice condensation nuclei present, we begin to transition over into ice. Ice crystals begin to form. And by the time you get down to around -20, pretty much everything's ice. Now there is a Schaefer point, which is the actual temperature that there'll be instantaneous homogeneous nucleation, which is around -36 degrees Celsius. But there are supercooled water droplets. So think about if you're a plane, if you're a pilot of a plane and flying up there, you could be running through water that's could literally freeze on your plane instantly because it's running at about a temperature outside of maybe -8, -9 Celsius. One of the things interesting about precipitation is it has the terminal velocity. We learned more and more about forces every week here, and we're going to learn about it this week. Gravity pulls the air down, pulling that snowflake down. However, friction resists it, so that eventually there's a balance reached. When that balance is reached, that's the terminal velocity of that snowflake. So how does precipitation form? There's a warm process and there's a cold process. If the clouds are above freezing, the collision coalescence. What does that mean? Well, one droplet begins to get just a little bit bigger and starts to fall. Well, what it does, it begins to hit other droplets and begins to collect them in more and more so that it continues to grow. Think about this happening millions of times up there in the cloud. They're your cloud. That's how the warm process works. Now, if the cloud is below freezing, there's something called the Bergeron-Findeisen effect. What is that? Okay, Over ice, remember we've talked about it in this last chapter, that saturation vapor pressure is lower over ice than it is over liquid. So that means that the liquid is going to be pushed. Remember, vapor pressure is just going to move towards the lower pressure. It's going to go towards the ice crystals. So ice crystals are going to grow at the expense of the water droplets around them. So the ice crystals are going to continually get bigger, where the water droplets are going to slowly disappear. That's the Bergeron-Findeisen effect. So now that we've seen kind of how precipitation forms, here is how it kind of doesn't make it to the ground. If you have high clouds, and I've seen these in West Virginia, I've seen them here, precipitation coming out, it looks like it's going to make it all the way down. It just never makes it. Drying occurs below that. You wind up with virga. There are different types of precipitation: rain, drizzle, snow. One of the interesting things about snow is it comes in all shapes and sizes. Here's dendrite, fairly big snowflake, occurs around anywhere from -10 to -20. There's some other ones that are right around 0 that are a little smaller. But notice all these solid prisms and even more solid. Try forecasting snowfall. If you're getting this kind of snowfall, the same amount of precipitation that might have occurred with this kind of snowfall would lead to extremely different amounts of snow. These palettes might only give you an inch or two, where if it was dendrites, it might give you 3 or 4 inches. The big difference on how you're driving and how the impact is going to be. So one of the things that always has to be thought about when you're forecasting snow is what type of crystals are going to be falling out of the clouds. Here you can see almost all precipitation starts at temperatures below freezing. We think about the clouds go up pretty high. So almost all are below freezing and start as snow. The Bergeron-Findeisen effect is in full force. At some point, as they're dropping down, temperatures get above freezing. The snow melts, forms a water droplet. That water droplet continues falling to the surface. In most cases, it forms as rain. Let's say there's an area just a little bit near the ground. Maybe you have a valley in West Virginia, for example, that's just sitting at 31 degrees this morning. And there's all this rain above it, though. Temperatures in the mountains are probably 35, 36 degrees at the top. Though the rain's falling down on top of the mountains, it hits this valley, and the temperature is just below freezing. What happens? You get freezing rain. Now, that gets a little bit thicker. Maybe now you're getting some sleet, ice crystals. And if the whole column stays at or below freezing, you'll get snow. You might get snow to around about 36 degrees sometimes, but it's difficult when you get to that point. But this is just, think about it, the layers of temperatures within the atmosphere in the vertical change, and that dictates the type of precipitation you're going to get on the ground. So you can see there freezing rain. Radar, it's one of the greatest tools. In a reflectivity mode, it allows you to detect areas of precipitation. It can detect some kinds of clouds. It can detect bugs. Believe it or not, along a cold front or a warm front, bugs tend to get pulled in. There's convergence of air. Bugs are pretty small. And you can actually detect those features sometimes on reflectivity mode. Velocity mode just takes the motion of air moving away or towards the radar. That provides with you a means to see circulations. It can tell you how the big picture of air is moving at different levels. It can also tell you if in a thunderstorm you're getting a circulation, which might lead to tornadoes. Here's your just radome. And it's a wonderful time to climb up these steps. I've done it a few times. I would prefer not to. I don't like heights. There's the Doppler effect. There's just an image of reflectivity. And there's the radar actually showing a weak circulation. And here's the tornado with some debris. And this debris that's showing up here, tornado debris signature, actually comes from something called dual pole radar, which is a very different radar technique. It was an upgrade to the WSR 88Ds, and the 88 actually stands for when the radar came out in 1988. So these are old radars you're seeing used out there. But dual pole has meant tremendously. There's something coming in the future, maybe phased array. Obviously, ships use it now for detecting things. Phased array is a wonderful thing because you can look instantly at every elevation within a storm, and you're literally getting a pulse back every few seconds. So you can really see the changes going on dynamically within a storm or within the atmosphere. However, phased array is extremely expensive. It costs about $1 billion or more for each radar. So it's not coming anytime in the near future. This is just another way of estimating rainfall using radar. We have cloud classifications, and I gave you some of that. Here's cloud streets. This happens in West Virginia all the time in the wintertime, where you get lake effect snow or mountain effect snow. You see these streets of clouds coming off the Great Lakes, pluming down all the way into West Virginia. I have seen some that have come all the way from Lake Michigan all the way down, and you can't see another cloud around them, but they'll just hold together and they'll come into the mountains in West Virginia and dump snow. So it's kind of neat to watch. Another thing you can do with moisture is fog. Think about it, if fog forms over a warm body of water, moving, winds are coming from the south, pushing the fog inland. I had this happen at a football game at Florida State. I was at a high school football game on a Friday night, and it started getting foggy. What was happening was fog was being advected in from the Gulf of Mexico. And by halftime, you couldn't see across the field because that much fog had come in. So with that, let's take a look at a couple things here today. Here's the current weather map. You can actually see there's a cold front, fairly cold at this time, up in Michigan and stuff, but it's all still rain. And you can see a good strong cold front that's moved off the east coast of the United States. You don't really see any satellite streaks, but what's interesting here to me is the moisture coming up towards that low up in Michigan, Minnesota. You can actually see moisture coming out of the Gulf of Mexico towards it. And here in Florida, moisture coming down from the northeast, literally coming into Florida from the Atlantic, off the northeast winds coming behind this cold front. If we were looking at a sounding today, for example, in Minnesota, you would see that temperatures are above freezing, so the temperature is rain. But look at it as it goes up. Almost all this sounding is right here is -10. So any cloud that's above this level, you can pretty well assume is going to have ice. Because of that, it's going to be doing the Bergeron thin Dyson effect. So almost the whole cloud is in that element. And that's what's interesting to look at the satellite. But with these upper air sounding, you can see where the ice begins to form. And it helps you with predicting of what precipitation is going to form, because you can understand whether it's Bergeron or maybe collision coalescence. Now, looking at Doppler radar today, we have a couple patterns going on here. We looked at that low up here. There's another one up in New England here. If you were just to zoom in on this Doppler radar, we'll take this one. Here it should come up in a second. And you can see it moving across the Great Lakes right there. If you were to look at velocity with that, you can see the radar is back here, and all this rain is moving away from the radar. So you can actually get a picture of the velocity from that. The wind is at that level. It's pretty much out of the southwest or west. Dual pole, I wanted to give you a couple quick looks at it. It gives you both a vertical and horizontal depiction of rain or clouds. And a lot of times it used to be very hard to differentiate. You can see a thunderstorm with very high reflectivities in it, and you think that there may be hail there, but you don't know for sure. So when you would put out a warning, you would say there might be hail. Now, what differential reflectivity does, it looks at the changes in shape. Hail is significantly different than a raindrop. And you can see right in this area, there's a tremendous change of shape going on of the precipitation. And that's hail that's actually occurring. If you want to look back at something else with this in dual pole can also depict melting layers. Again, there's a change. Ice is not going to look the same as water. So it can actually pick out the level that the precipitation is melting. Oh yeah, here's some strong updrafts which are pushing super cold water higher in the sky. So there's actually liquid there mixed with ice crystals. Kind of neat to see when you're looking at it, because I could never have seen this with base reflectivity, but now I can tell you that in this level is about the height of the 0-degree isotherm. So everything below that's going to be rain, everything above it's going to be snow. And finally, there's one other neat trick that dual pole can do that we didn't use to. Dual pole is also really good for estimating precipitation, but it also can actually pick up debris. You think about it, sizes of debris are different. So that's a way when tornadoes occur and they put insulation up in the air, whatever, we can pick that up now with dual pole radar and give you a pretty good idea that there is a tornado occurring. So if you have any questions, please don't hesitate to